Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Professor Gert Cauwenberghs from the University of California at San Diego talks about neuromorphic computing. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking to Professor Gert Cauwenberghs from the University of California at San Diego about building very large neuromorphic systems. One in particular with 160 million neurons you may soon be able to access yourself. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. As you'll hear, Gert and I have in common that we both started off focused on optics and photonics, but he's gone on to become a leader in the development of massively parallel neuromorphic systems that use both analog and digital electronic components. In this interview, we focus on perhaps his most important contributions to the field, creating reconfigurable and scalable computing architectures that can work flexibly with different workloads. However, we'll also have time for his newer work on tiny devices with huge biomedical potential. There are links to his work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. Gert Cauwenberghs, welcome to Brains and Machines.
Thank you, Sunny. Very nice chatting to you.
Let's start by talking about how you got here. What is your technical background, and what attracted you to neuromorphic approaches to computing?
Wow, that's a long while ago. So I arrived at Caltech in 1988, unfortunately just after Dick Feynman passed. But I was fortunate to be there when Carver Mead just started the field of neuromorphic engineering. I was supposed to work on quantum electronics and nonlinear optics. My advisor, Amnon Yariv, is really a leader in the field. And that was all very exciting. But I got even more excited about this concept of building brains in silicon. And I was taking John Hopfield's course on collective neural computation, which really was wonderful. And then Carver Mead had this course on analog VLSI and neural systems. There we had Misha Mahalal, Toby Delbruck. They were my TAs. And it was a very interactive, interesting, stimulating experience. And I was able to make my own chip. It was fantastic. I knew this is what I want to do for the rest of my life. So through Caltech, then I went to Johns Hopkins, was working there with Andres Andreu, Ralph Etienne-Cummings, and others on transcending neuromorphic engineering to the next level, including biomedical neural interfaces. After Johns Hopkins, now I'm at UC San Diego, even broader, expanding my field in neuroscience, computational neuroscience. That's been very exciting. So neuroengineering is where I am now in biomedical engineering.
So I'd like to talk about three of your important contributions to the field during this interview, and actually a fourth one, which is going to make it very packed, but let's have a go. So we're going to talk about the Integrate and Fire Transceiver Array, IFAT, your memristor-based compute and memory chip for implementing neural networks, which is known as NeuRAM, and your hierarchical address event representation system known as High-AER, which is intended to allow AER networks to scale to the size of biological brains. We'll take them one at a time. Let's start with the Integrate and Fire Transceiver Array. What problem were you trying to solve, and what insights did you embed in your solution?
Well, that also goes back quite a while. When I was at Johns Hopkins, we started this concept of building those brain-like systems. And very soon we realized that, sure, you can design a chip that does one thing. You have neurons and you have synapses and you make the network. And then you realize after you fabricate a chip, you're stuck with whatever network that we have. You can't change the number of neurons. You can't change the number of synapses. The network topology is all frozen in the silicon. And it's great to do silicon-integrated circuits, but that's one constraint. You can't rewire things on the fly, at least not in a physical sense, right? So we realized, and others realized this too, you can just have reconfigurable connectivity, virtual connectivity in a network. This is the address event representation, right? So where connections are actually implied, not by physical connection, but by basically an address that encodes what a neuron is. And then you can make synapses in the virtual domain. When a neuron fires, it sends a request coming out. That's an event. You register that. And then outside of the chip, you can figure out, hey, where does this event go to? So then you wrap it around. And that could be in standard asynchronous digital logic or anything that you want to do. You figure out where that event goes to. So that's the concept of an integrated fire array transceiver, right? As a system, you can have spikes coming in. Those are presynaptic events, right? Then you have spike going out when a neuron fires. Those are postsynaptic events, right? And so the connection between the two is then taken care of externally to that fabric. And so within that fabric, we have those analog continuous time dynamics of what the neurons are doing. We have even dendritic dynamics that are captured, say, with a proximal site, a distal site, and then the soma. And when neural events coming in, those are events that are routed, say, to this proximal or distal side with different types of synapses, which we also implemented where a neuron is excitatory or inhibitory depends on the reversal potential. The time course of the synaptic activity, that's another parameter that we can change in analog continuous time domain. And then when a neuron fires, you have a certain threshold for firing, you have a reset potential. So all those things are implemented in the analog domain with this neural synaptic circuits. But the key is that neural circuit that receives spikes and an output spikes, that's not any different, say, from a memory element in an array. It's addressable. You have an XY address you come in at, and you have an XY address where you go out to. And so then this event-based representation allows you to very efficiently make almost any network. Because what we implement at the neuron level is the reconfigurable dynamics of what synapses do, but now you can actually route any number of synapses to that neuron with the different types that you specify in that circuit. And that's basically what the IFAT chip does. Yeah.
So it's interesting to consider the trade-offs that you have to make when you're putting in all this reconfigurability into a system which wasn't there before, and thinking about the technologies that you're going to use to do that. And obviously, interconnection fabric is a subject that we're going to come back to in your next two projects. So how do you think about what you want to do, say, digitally, what you want to do virtually, and what you want to do in the physical layer? And how does that pertain to IFAT so that then we can compare that with your other projects?
Yeah, that's really a core question in the field of neuromorphic engineering in general, right? So do you do it analog? Do you do it digital? Is it going to be continuous time, discrete time? And there have been different trains of thoughts of how to do it. I've come to the conclusion over many years that you just don't pick one. You have to have a hybrid to make things efficient. So you want to do the core computation that is coupled to memory in analog, because that's where you can get great density and great efficiency. And you want to get the highest efficiency in the synapses, because after all, you have way more synapses than you have neurons. So the synaptic circuits, the interface into the neuron, right? Those have to be analog in continuous time, in my opinion, and that's what has been working out the very best. On the other hand, communication, neural communication, better is digital, right? That's where you have this asynchronous, or sometimes just clocked is fine too, right? And then you can have some other large-scale connectivity, which we'll talk about a bit later on the higher hierarchical address event routing. Now you build this network traffic, this communication systems, right? And that's definitely digital. But at the core neuron level, we'd like things to be actually quite analog for the synapses. Now, does a neuron have to be digital or analog? We have gone back and forth. We have done both, and we have good results with both, depending on what you want. If you want truly very high level of detail, and if you care about building a system that is truly physical, which maybe even interfaces to biological neurons, you have to make it analog in continuous time. And in fact, you might as well take advantage of the natural noise, the thermodynamic that is naturally present in the circuits. Biology harnesses noise, and so neuromorphic designers can actually take advantage of noise and have it there as a feature rather than a bug in designing circuits. And so then you have the advantage of a truly analog circuit that has all the good stuff that you have in real brains. If you want an exact answer for an AI application, maybe a digital neuron is better, because then it's reproducible, you get always the same answer. And we have done both. But still, I think your synapses should be analog, and that's basically what we do.
So let's talk about NeurM. Now, there's a good example. So the core of the computation is done in analog, but then there's routing and all sorts of clever tricks that you do with the transposability of your array to give you reconfigurability. Now, it's a complex system. I took a long time reading the paper, and I don't think we can go through all of the innovations that you made in that particular system. But maybe you could pick out 2 or 3 that you think really illuminate important principles.
Absolutely, yes. And NeurOM was actually a major undertaking. In fact, it was a great collaboration with many people. So Philip Wong at Stanford has been a great collaborator for many years. And in fact, we have several other students. They're now faculty, Raj Kumar Kupendran, Siddhar Joshi, right? And of course, Wei Wan as the lead of this effort. As a Stanford PhD, he's now a CTO of a company, AI Zip. So that was a major undertaking. And so this is a good example where we had walked out of the typical framework of neuromorphic computing, the classic one that CoverMeet started, where it has to be subthreshold, analog, continuous time. So there is a different flavor of neuromorphic. We didn't even call the chip neuromorphic, we called it AI or AI on the edge. But it's still analog inside, and we have very efficient charge domain CMOS circuits that are much more robust to imprecision variability than those subthreshold analog current domain circuits. Some people call it memristors. We call it resistive random access memory. It's the same thing, right? It's basically those 3D integrated technologies on top of the CMOS, where you can have these resistive memory elements that can change their conductance based on history, right, of what is happening. And so we have this crossbar arrays of synapses on top of the arrays of neurons underneath, right? So you have this quite coarse grids of neurons on the micron scale in the CMOS, and then you have more nanometer scale synapses in these crossbars on top. So the way we made it work is to have this very efficient CMOS circuits interface with the synapses in such a way that we can overcome several limitations with previous realizations. One of them was voltage sampling rather than current sampling. A typical problem with this crossbar arrays is that, sure, you have those intersections of conductances, just like in the real synapses in the brain, those are conductances, right? So you have to apply a voltage across them, like a reverse potential, and then you get the current across the membrane. But to get a voltage across the memristor, you want to apply voltage on one side and a reference voltage on the other side. And you want to measure the current at the reference point to actually collect all the currents from all the synapses that come in. And so measuring a current at a given voltage is a hard problem. That is a very energy-consuming process. And building what is called a transimpedance amplifier is very power-hungry and not efficient. So you spend more power in that TIA, this transimpedance amplifier, than an entire array. So we built some very efficient circuits that actually do this without a TIA. And this is a voltage sampling technique that we have. And that made it extremely efficient. Normally, you wouldn't think of the memristors to be very energy efficient because typically, the currents they consume are milliamps, right? You have milliamps of current, so you would assume, well, easily get watts of power. No, actually, we're able to bring this down to milliwatts, and for each synaptic operation, how much energy does it consume? We measured it to be 13 femtojoules per synaptic operation each time a neuron activates it, compared to about 1 femtojoule on average per synaptic operation in the brain. And I can explain you why this. Basically, our brains consume, roughly speaking, 10 watts, 15 watts of metabolic power, right? We have 10 to the 15 synapses, roughly speaking. And neurons fire about 10 hertz, so 10 times per second the synapses are activated. So that's basically 10 to the 15 operations per second per watt, right? And that gives you then 10 to the minus 15 or this femtojoule, right? So that's how efficient our brains are. So femtojoule per synaptic operation each time a spike causes it to activate. So in our chip, we measured 13 femtojoules owing to the way we implemented the circuits. And this is only one of the things that made it efficient. What NeurOM is able to accomplish were 3 important things that are actually the holy grail in the way of AI is on the edge. Not only do you want to have really great performance in what it does and great flexibility in what you do in a compute, but you also want to make it efficient. And you have to choose normally, right? Either you have very efficient hardware, but then you cannot do X with it and you can't do Y. Or you have something that can do X, Y, Z, anything, but then it's not efficient. So NeurOM is able to do all 3 in once because we have this reconfigurable hierarchical additive routing kind of architecture where you have the cores that are very efficiently implementing this resistive random access memory with CMOS neurons underneath, very efficient at femtojoule per synaptic operation efficiencies. And then we have this very efficient fabric of reconfiguring that and training it that we implemented in NeurOM that made it versatile and high performing. So that's basically an important aspect of what made NeurOM what it is.
I also wanted to ask you actually about MEM capacitors, because when I came to visit you at your lab last year, you said actually the way you want to go is not MEM ristors, but MEM capacitors, because that way you're not wasting any power, because every time you have a resistance, that implies you're losing energy. Yeah. So how much lower can you get with MEM capacitors than with MEM ristors?
You know what? We went back and forth between different realizations of what makes it efficient. We think actually, even with those memristors, we can still make it efficient to the point of approaching the nominal efficiency of synaptic transmission in the brain of the femtojoule per synaptic operation. And in fact, we are close to doing it with the latest implementations that are now in the works. We're taping this out now, and we'll see this later. So a femtojoule per synaptic operation can be accomplished even with these memristors, even though they are lossy. They are resistor devices. They have Ohm's law will tell you, yes, there's going to be some current, some voltage, and that, so Johnson, in addition to low noise, there's also a lot of dissipation of this happening there. Yes, so you waste entire V squared over R, right? That's the power that is consumed for each of them. But fortunately, there's a capacitance on that node. So there's a certain bandwidth over which you do computation. And the bandwidth can be matched based on the RC time constant that you have of the interface, right? So sure, if resistor is higher for the same voltage, there's less power consumed, but it takes longer time for RC to settle. And there's something called the equipartition theorem that tells you no matter what, the energy that is consumed is going to be invariant. It's going to be just CV squared. So the magic is even with the memristors, we get CV squared energy that is consumed. And so if you make the parasitic capacitance small, which we have actually accomplished in some of our implementations, if you have a femtofarad of capacitance on a node, you still can only get a femtojoule of compute energy. And the brain does the same, I would say, probably, right? It figured out that the limit where it can operate is probably also the same level of capacitances, femtofarad capacitances for the actual synaptic terminal, etc., right? But now, can we do better? Can we outsmart nature? Of course we can't. But so we actually managed to even get around that CV squared energy, the fundamental limit that you have of thermal energy that you consume, with those adiabatic energy recovery style, right? Those are charge domain circuits. Those are like capacitors, but they're actually non-linear capacitance because basically charge moves back and forth between the channels of between two electrodes. And that process is intrinsically loss-free as long as the charge gets conserved. And in fact, in the latest silicon insulator process, we can actually ensure we don't lose a charge. That is even better. But then the problem is, okay, you're driving those two electrodes, right, to move the charge back and forth at zero loss of energy. Only if you can actually drive that line at zero energy. And that has been a problem with most drivers because most digital circuits consume CV squared times the frequency F. Because even though, strictly speaking, CMOS has no static energy, has dynamic energy, and that's due to the fact that with a standard CMOS inverter, right, you're delivering electrons, say, from ground, and you're taking them from VDD, from your supply voltage. And so the electrons lose that entire energy, VDD, right? So the charge is a C times V. That energy of that charge is lost. The potential difference is just entirely lost. And that's why you get CV squared, energy loss, each time you move charge back and forth between those two levels, right? And we use area recovery logic or different style of CMOS circuits that actually recover the energy with this adiabatic hot clock. So rather than having a static supply, now you have a hot clock that goes between those two levels, between ground and VDD. It oscillates the frequency. And the frequency can be like a gigahertz, the latest implementation, right? In earlier work, it was like a few megahertz, but now it's like a gigahertz. Fast, right? But it's still adiabatic. So the time comes are much slower than a nanosecond. So you still have low loss in this hot clock. And so then basically you never close a switch unless the voltage is zero. And that's a trick that we use in adiabatic energy recovery circuit style. And that way we manage to basically recover most of that CV square energy. In fact, with the 3 femtofarad capacitance in this charge coupled devices are actually down to 100 attojoules or even less. Basically a factor 10 better than what the brain is doing, normally speaking, owing to this recovery of the energy. So things can get quite exciting. So in principle, we can have a brain that is the size of, let's say, a cubic decimeter, and that system can do now what the brain can do, but not at the efficiency of, say, 10 watts, but now go down to 1 watt or even 100 milliwatts. So that's a feature. Now you can have a whole farm of those things doing, in principle, brain-like computing at energy efficiency is even better than the brain. But that's still far out of there. So we're making good progress in that direction.
That's fantastic. Okay, so we've been talking a lot about processing and processing efficiencies, but I want to go back to communication now. So I want to talk about hierarchical address event representation, and specifically, what was the problem with regular AER, and how does hierarchical AER work?
So the conventional AER framework, as it was originally formulated and implemented in the first silicon cortex, Misha Marwald, Steve Dice, Rodney Douglas, etc., right? It was great, but the hierarchy was flat in the sense that there was mostly one bus that would communicate events. So when a neuron fires, it makes a request and those events are communicated over the bus, but only one can communicate at any given time. So there's time multiplexing involved. So clearly there's a serialization there, even though the brain does it massively parallel, there's a serialization in that concept, right? And how fast can you make it? So initially it was fine because you can make buses gigahertz easily, and neurons fire about, I guess, maybe 10 hertz. So you can put a lot of events on that bus without, I guess, much of a conflict. But once you start building systems that have to scale towards truly brain-like computing, again, there will be bottleneck, right? So you need many of them in parallel. And so our work has been to make the hierarchical architecture just the same way as the white matter is organized in a hierarchical fashion. So you have two hemispheres of the brain, and within each hemisphere you have again a division, right? Eventually you have the microcolumns and the microcolumns, right? So you have different levels of hierarchy of the white matter connectivity that is then implemented in these different levels of scale in which higher hierarchical address event routing will send events, right? And so very simply, at each level of scale, we have what we call relay neurons. Those are the proxies of the actual events down at the leaf node of the hierarchy that are representing that activity at that level. So when a neuron fires, it goes one level up, and the relay neuron there that will basically then figure out where it has to go to. But then other events may have to go one level up. A level up basically means at that level, there are other relay neurons that connect to their peers at that level, right? All the way to the highest level. So then there we have those few neurons, not too many, that connects between the two hemispheres. So the concept of the relay neuron is one in which you have this hierarchical connectivity. So the way that connectivity is organized is network topology rather than flat, right? And so that is very efficiently implemented in the brain. With higher, we also implemented this in a reconfigurable manner, in which we have some stages or some process by which we partition the actual network that we want to implement and map it into this very efficient multi-scale architecture in such a way that we minimize the connections that have to cross at each level in the architecture. But this then allows it to very efficiently implement this connectivity. And it so happens that the bandwidth is preserved at each scale, which means if you make a network that is twice bigger, let's say now a brain is twice bigger, you just have to make the top level in the hierarchy, just add one more layer if you want, right? And the bandwidth at each level of the hierarchy is preserved because at each level we still have the same bandwidth. And the same thing is true in the brain too, right? Of course, you have to go farther away, but there are fewer neurons that need to go that far away. So we have this typical tail of a distribution. Most of the neurons connect very densely locally, but then the farther you go, the sparser the connections get, and the bandwidth of the system is still totally scalable. And this is how we basically build our hardware. And that's how you have the latest hardware, say, on the higher spike system, right? Where we actually implement this in a truly reconfigurable fashion, where the highest level of the scale would be, say, the supercomputer center that connects this to another node, right? To the internet. After all, the internet is a great way of connecting events too.
So I wanted to ask you about high AER spike. So that is a system that is running on FPGAs. So it's essentially a kind of simulation in the sense that the processing part of it is not done in a physical layer that's implementing some kind of nonlinearity. All of the nonlinearity is quite efficiently still done in software, essentially. So you can program in the kinds of spike firing that you want to see and all of that. Can you talk a little bit more about that system, perhaps in a more elegant way than I've just done?
Yes, absolutely. And you bring up an excellent point. So what is the role of software in all this, right? Because we can build this very efficient hardware, but if all it can do is generate nice, beautiful plots on an oscilloscope, it is not very useful. And so the biggest effort typically required to make those things useful is to actually in the software domain, making sure to interface to the hardware. right? We have all those fabrics. And so in higher spike, actually, we have all those Python code that interfaces to the hardware and this FPGA, this field programmable gate array hardware, in such a way that it's totally transparent to the user. The user doesn't even have to be bothered with the fact that there are those FPGAs sitting in that server room, because the code that the user writes is just the same Python code that they would write normally, just run their software, right? And so we make it transparent. And how we manage to do that? Well, so we have this software that runs on Python, and we have a certain code that we provide, right? And so as long as the user uses the same libraries, everything works perfectly fine. They can run it on their laptop. But now, once we run that code on the hardware, on the server, this will interface to the FPGA hardware and actually run those parts much more efficiently. So right now we have the full capacity of the system with 40 FPGAs is 160 million neurons and 40 billion synapses. And they all run in parallel. Parallel here basically means all the FPGAs, we have 40 FPGAs. There are 8 FPGAs on each server. They're all massively interconnected, both over the internet at one level and also over Firefly, direct connection between FPGAs within each server too. And then within each FPGA, we have 32 cores. Right now we're using 16 of those that have direct access to what is called HBM, or high bandwidth memory. And that has been a great invention over the last decade or so. It's a much faster bandwidth of memory than the conventional DRAM that they have. And so that's how we get actually 0.5 terabyte per second bandwidth to the memory on each FPGA. So together we have this massive bandwidth. And memory access is the key. Memory bandwidth is all you need really for doing great neuromorphic computing, right? So basically that's the full capacity of the system. What we have running right now for the user to interface is a one-core version that only has just 128,000 neurons and just 4 million synapses. Still amazing what it is. And now we are finalizing and making public available our 16-core version. That's really fantastic, right? So 4 million neurons, 500 million synapses. So that's the scale of things, right? And so we get this massive parallelism by which it runs on FPGAs with the cores. So each core is sequential because the memory access of the HBM type of memory is a sequential process. But still, it's very fast, right? And there we implement the equivalent of IFAT, right? We go through these tables of memory connectivity in HBM to define how the neurons are connected. And the FPGA does all the nonlinear processing, right? All the functions and combining all the synaptic input and integrating all that, right? And those neurons are stochastic and leaky, just like real neurons. They can ask, hey, how do you implement stochastic neurons on a digital computer? Hey, we know how to build random number generators very efficiently, and that's something actually in my thesis even, and nobody seems to know this. People are still building those very complicated random number generators. We have a very simple way of generating random numbers, massively in parallel in digital, right? Just with 2 registers for each bit. And that's how we can generate billions of random numbers all in parallel in digital, right? And then we have other functions implementing the integrated fire and the leak, right? So yeah, neurons are not very sophisticated model. It's not like IFAT where we have all the different reverse potentials and time constant of the synapses, right? But it's still amazing what they can do. Yeah.
So my understanding is that this is part of this new project called the Neuromorphic Hub, also known as Thor. So this is a whole bunch of different kinds of neuromorphic hardware or neuromorphic simulators, depending on which it is, that are going to be made available through the internet for various users. Can you tell me both a little bit more about that project and also how these neuromorphic simulators fit into advancing neuromorphic technology, in the sense that these are generally digital simulators and neuromorphic is doing interesting stuff at the physical layer, as we've discussed earlier?
Well, we had a first NSF project that funded Higher Spike. That's what built this infrastructure, right, for the community. It is now available over the Neuroscience Gateway. But we were also very excited to have this new project called Thor, led by Dirisha, right? Kuditi, Catherine Schumann is also part of it, and others. So we have a great team. So we have the Supercomputer Center now at the University of Texas at San Antonio, where we have all these different systems being hosted. Those are the Spinnaker 2 system that is now being configured there. We have some other systems. So Luhi 2 is one that we also wanted to get up and running. We're still getting that up. And so we have all these different infrastructures, right? IBM is another great one that we're planning to incorporate. So those are great systems that are developed by companies that we're now hosting for any user to be able to access that and to have this lower access barriers of entry to actually do neuromorphic computing at scale. Now, the higher spike system is actually running in this supercomputer center here in San Diego, but we're linking that to the fabric as well. Yeah.
Now, I'm assuming that the benefit of a system like high AER spike is that you can test out different configurations of networks, different kinds of neuron models, that kind of thing, and then figure out, hopefully, what kind of chip you would need in order to run that efficiently. Your software that you were talking about earlier, is that what that's trying to help you get towards?
Absolutely. And so the typical problem, as I mentioned earlier, with neuromorphic computing or neuromorphic engineering has been you build a chip and that's one thing, and it can only do that. If you want to do anything else, you're stuck. So the concept of having truly reconfigurable neuromorphic computing has been bothering us for a long while. And so now we made this as a resource to the community so that anyone who has a new network they want to explore and try out, they can do it on this hardware as long as it conforms to a few very simple basic assumptions, right? So that you have a network, you can connect it any way you want. So you can have any topology of connectivity, but you see the neurons, they're getting fired, leaky, they're right, noisy. And those are parameters you can all configure, right? And you can also configure the synaptic strength, etc. When it scales up, it will be billions of synapses and millions of neurons. So that's what you can do. As long as this is the constraint that you can live with it, you can now do anything. You can even interact with the system in real time and change the weights, right, through your software and observe, say, plasticity or some algorithms that you're observing. So this becomes a platform that the community can develop and expand on collectively, because if you use it, you have to commit to share what you built to the community, that others can replicate what you did and further build on it. So this is a way of ensuring that we're not just silos and do our own thing, but that we can all work together. And so this is our vision, both in Thor as well as earlier we did in Higher Spike, of building that community and make that resource something valuable by which the community can really make progress collectively.
So now I want to change to something completely different before we finish. You're doing some really interesting work in wearables in the ear, or earables, as you like to call them. I'm not sure I'm down with that word yet. So the idea is that through the ear, you can get access to all sorts of really interesting signals, some of them optically, some of them electronically, some of them through chemical sensing, sweat, and so on. But also that you can stimulate the brain through nerves that are around that area. Now, I'd like to hear you say just a little bit about how you got involved with that project, and also whether you see it as going towards neuromorphic in terms of the circuitry at some point.
Absolutely. And that also goes back with a long history. So in fact, when I was at Johns Hopkins, it was Nidhish Tekor. One day he walked in my office and he was saying, "It's great, all those neuromorphic chips you're doing, that's wonderful, but why don't you do something that can actually benefit humans and health, right? And build circuits that efficiently interface with biology at scale." And sure, I was sold. And so a very important component of our work and others that followed us has been to take neuromorphic engineering one step further. We call this now neuromorphic integrated bioelectronics. In fact, I teach a course on a topic, and it's on the web. Anyone can access it. If you search for neuromorphic integrated bioelectronics, Google will give you the first hit, and all materials are posted. And this is our vision, right? How you integrate both. Neuromorphic engineering not only has a really great way of building very efficient chips for computing, but also because modeling the brain and interfacing to the brain, because the same circuits that are highly efficient with very great noise energy efficiency for compute are also very efficient for sensing and stimulating, right? And so we built those circuits that also equate or approach the efficiency of, say, how neurons interface to the retina, the cochlea, etc., right? So now we have circuits that are very efficient also to actually record potentials and stimulate signals, right? So all the way from very efficient circuits in intercellular recording, that's where we interface neuromorphic circuits directly in vitro with their counterparts in biology for biohybrid circuits, the silicon and the actual biology circuits talking to each other. all the way to the other extreme. We have circuits that are extremely efficient at sensing and modulating brain activity, even without contacting the brain, even without contacting the skin. So there's an extreme opposite of totally unobtrusive, non-invasive physiology and metabolic systems where you can observe activity at a small distance. And in fact, one of my former students, Mike Chi, he was even commercializing this with his cognionics systems, CGX, with his headsets for efficiently recording brain activity with wireless interfaces. But now the latest is even in the ear, we can record brain waves without having to be anywhere close to the brain, making just dry contact to the skin on the ear canal. In addition to some other sensors, we can also measure different chemicals. This so happens that the ear has all these different signals, whether it's this brain signals or this electrical signals, but also chemical signals that are very unique in the ear. And we can observe all those on a flexible platform with circuits that are mounted on an ear pod in the ear. And so now you can have both the capability of recording activity, but also activate activity, because that's why I call them earables or hearables. You can also play sound. And what we're doing now is we're actually closing the loop and playing sound that correlates with the brain waves that we measure in such a way that we can drive the brain towards more desirable states. Say if you want to fall asleep, you have insomnia, you can't fall asleep. You can have this active lullaby if you want. So play sound that drives you in this deeper sleep, this slow wave sleep, just in this neurofeedback scheme, right? Another very important thing you want to do is tinnitus, where we are then driving sound in such a way that we can improve on the biomarker, so reduce then the tinnitus. And that's a very hard thing to do, but that's a very important thing that we want to do. Alzheimer's is another thing that we're doing in collaboration with Alex Khalil. Very exciting things, right? So playing sound that will actually keep the brain active, right? These gamma waves. So those are very exciting things that we can do with neurofeedback once we can measure those brain waves. And so neuromorphic computing can take another angle to this, right? Where we actually have a loop where we can have the brain actively involved in the loop that is neuromorphic for doing not just computing, but also doing intelligent control action, right? For neurofeedback and helping the brain.
Fantastic. Gert Cauwenberghs, thank you so much for coming on to Brains and Machines.
Thanks so much, Sunny.
Thanks, Sunny. So the interview with Gert Cauwenberghs was so packed with knowledge that I had to listen to it twice. I love the fact that anyone who wants to use the supercomputer has to commit to sharing what they've built with the community so others can replicate it and build upon it. For more about Gert Cauwenberghs' work, please go to brainsandmachines.net. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University. So let's start with the very straightforward first question. Ralph, does the neuron need to be digital or not?
So I'm very happy that we got to speak to Gert. Gert is, has been a friend forever. In fact, he was one of the reasons why I came to Hopkins. He was one of the people that brought me there. So I'm very keyed in on what he does, all the work that he's done through his life. One of the presentations that I remember him giving at Telluride Neuromorphic Workshop was showing that a neuron is, in fact, the data converter. It's a sigma delta converter. And I remember him going through the process. So that's his perspective, right? So you got the integration, and then after a while, you get a firing. And that firing causes the change in the way the integration is done. So there's a loop back, essentially the feedback is done. That's where adaptation comes in. And based on the statistics of the spikes that comes out, you are able to get some idea of what the information that came in. So that's been Gert's perspective for a long time, and I love it. Does the neuron have to be digital? In that context, it is, right? But I think ultimately for me, it has to be digital in the sense that you are working with such small power supplies, right? The natural neuron is 150 millivolts, kind of peak to peak. When you get to that level, you are so close to noise, thermal noise in materials, that the only way that you can really get information and not it be completely overwhelmed by noise is this notion that you have to use time as your indication of information, right? So interspike intervals, right? At that point, your neuron is just a spike producer, right, at one level, so binary. And then you look for the interspike changes. That is where the actual code lives, and then multiple of them and populations and so on. Gives you a richer code. So as we build more and more and more power efficient systems, that we go as smaller and smaller and smaller power supplies, I think our neurons will look more and more and more and more digital in nature.
But is asynchronous really digital? I mean, we call it asynchronous digital, but is it really digital? Is it meaningful to call it digital when, to me, digital implies, ones and zeros with specific numerical meanings? These do not have specific numerical meanings, right? They're part of a very sophisticated time code, just something that happens to spike at a certain level, but is asynchronous. I'm not happy with calling that digital.
So, okay, two things, I guess, right? So we agree that number one, the binariness, if you will, of the spike is at one extent digital, if you will, right? It's 1 or 0, there or not there. The time between spikes, ultimately, like everything, is bounded by what is the shortest time constants that we have in our system, right? The shortest one is going to be that resolution at which we can resolve the time between spikes, right? So whatever's reading it, whatever's decoding it, has to have that notion in mind. Otherwise, I'm not going to be able to tell the difference between, let's say, the number 10, which takes, let's say, 10 times the minimum time constant, and the number 7, which takes 7 times the minimum time constant. So in that sense, it's counting in units of the minimum time constant. So even...
No, it's not. I do not accept that. I do not accept that. So we've got a minimum bound and a maximum bound that we agree on. And I would argue that it is continuous.
I don't agree that there's a maximum bound. I think that's...
Well, so for instance, with Loihi, my understanding, and I don't fully understand Loihi enough to be definitive about this, but my understanding from talking to Mike Davis, we haven't been able to talk for the podcast yet. I hope he will accept that invitation sometime. But is that, for instance, it is mostly asynchronous, but eventually there's a point where it's like, well, even if there's been nothing, we're going to call it a day. So it's kind of got a final clock to it. But if something is asynchronous, it is continuous time within bounds.
But again, you're using a digital example as the example here, right? You're saying the Loihi, right? But Loihi is not, there's nothing profound about it itself, right? I mean, I would say there's nothing that really bounds you other than noise. So we take another example, which is the octopus retina that we did way back when, where we're converting photons into signal. At the end of the day, you cannot do anything more than one photon, right? One photon is a quanta. You can count photons now, right? Tuk, 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 and you get a number, and that translates into time. How long does it take before I get to the threshold? That is done in terms of counting photons, right? Well, in the similar thing in the electronics, we can count electrons, right? Putting one electron on one, 10 to the minus 19 femtofarad capacitor, that will give you a count of each electron that comes in. And electrons are quantas. You can count them in digits.
Yeah, I'm not arguing about the signal. I'm arguing about the time.
But we convert time into a signal. The capacitor does that, right? That's exactly what we're doing. We're taking photons or electrons over time and converting it into a signal. And it's a counter. Top, top. Anyway, it is a manifestation of the whole thing, right? We can look at time as a representation of signal.
I'm having flashbacks from my PhD here, Ralph. Flashbacks.
But
this is what my PhD was all about.
Sure, but it's not a negative, Sunny.
If we start talking about how Planck's time is what makes it digital, then I'm going to get very upset. Giulia, I think you're just pushing us to argue. I think you're picking these questions because you want to see us arguing.
But I knew it and I wanted it.
But I don't think it's a negative, Sunny. I think there's different ways of considering it. Just like in an electron, you can consider it as being a particle or a wave. A wave is continuous and a particle is quantized, right? It's the same kind of thing, right? You can look at the impact of time, the way that which that time changes in a continuous system. And you can look at it as overlapping of little quantas, or you can look at it as a continuous, right? It doesn't mean that one is right and one is wrong. It just means that it's a different representation of the whole thing.
Okay, I'm not going to interfere. I'm not going to interfere. I'm here like a student learning. Anyway, let's go on. So we know that Neurobench had different track. They had algorithm track and system track with algorithm metrics and system metrics. Now, I want to focus only on the network size metric. And recently I had the pleasure to be the discussion chair for the IOP Neuromorphic Computing Engineering webinar. And Elisa Donati raised a very good point that I want to bring here. So she's saying having more neurons, having more units that are computing your information does not equal to having more intelligence, right? Because it depends on the network itself and the structure of the network itself. What do you think about it?
Yeah, I mean, I think that's fairly accepted law now, right? In the sense that the synapses is what we say is the more important component, right? So we still somewhat neurochauvinistic in the sense that we always talk about my system has 10 to 11 neurons, your system only has 10 to the 9 neurons. Mine is better, right? We're still talking about that, but in the end, it's because that usually translates to a multiplying effect, which says that, oh, but each one of my neuron has 10 to the 3 synapses. So therefore, I have the potential to make even bigger networks, bigger connectivity than the other one can, right? So that's, I think, where that neuron counter comes from. But I think that ultimately it is the number of synapses or the dynamics of the synapses and dendrites and all those things that come up to basically make for more interesting networks that can then solve more complicated problems.
Yeah, I just wanted to add that it's about computational complexity. It's not about raw numbers of neurons. So there's some really complex, interesting, dynamical neurons. You cannot compare like with like. I mean, probably some of these are orders of magnitude more computationally complex and can do more than some of the simplest neurons.
Yeah, like the integrated fire, basically, right? Just that there's one thing. But if you have Izikevich or Mihalis Nibur and you can change some parameters and do all these different faces. I always like to think about it as well as a RISC versus a CISC computer, right? RISC is very simple instruction set, but you can go fast because you can do a lot of it quickly, right? CISC is a very complex instruction set, but you use less of it, but it's maybe a little bit slow, a little bit more crunchy because of you have to do so many steps. So that would be different flavors of neurons. But in the end, exactly what Sunny says, it's a computation that's being done in these two things. You know, if you can do more with more complicated neurons, then that's a little bit better. But if you transfer that to synapses and you can do more with synapses or dendrites, so all that put together, then you get even more dynamics, even more behaviors there. So I fall in that, I guess, hole or in that gutter as well, right? I'm always talking about, hey, my system can do more neurons per square millimeter than anybody else, right? But at the end of the day, it's a metric. And we have to put it in context. Doesn't stand by itself.
If I can add another point is also having a smart connections among your units more than having a number of units. But yes. Okay, so I really liked Sunny asking how do these neuromorphic simulators fit into advancing neuromorphic technology. Neuromorphic is doing interesting stuff at the physical level. Strictly emulating, you lose the possibility of the computational power. But simulating, you lose the interesting stuff on the physical layer. So this webinar was team emulation, Jennifer Asler and Elisa Donati against team simulation, Emre Nefci and Catherine Schumann. Where do you position yourself?
Yeah, it's a good question. I mean, I think I believe in both in a sense, right? I'm going to sit on the fence here. Okay, I wrote a paper back in 98 or whatever it was. It was at Sterling, where I argued for that same point, that do things in digital that are good in digital and do things in analog that are good in analog, right? Transformation of signals from the physical world into any code that you want to represent it is an analog process, and that has to be done in that way, right? And that you cannot really simulate, right? That transformation without losing the noise, without losing all the variability that you have there. On the other hand, once you got it into the electronic domain or optical domain, whichever it is that you're using, the computation that you do there, now the human has his touch. You know, he can be the puppet master. And then that's where the simulation can come in. So it's hard to simulate the front end, but the middle end is easy to simulate. And flip that the other way, and then you can do computation beyond that.
I want to bring in my favorite expression in neuromorphic engineering at this point, which is the analog shell. So the physical world is analog, But at some point, you have to transition probably into the digital world so that you can interact with all of the digital systems which are out there that your machine is going to want to interact with. And then you go back again. And to me, the interesting thing is how deep, how thick that analog shell is, right? How many processes can we do before we hand off something that's a little bit more abstract to the digital system, and where we've taken away a lot of the pain of processing that signal? And that is an ever-changing point.
Yeah, agreed.
Let's stop it here for today. Thank you, Sunny, again for yet another great interview, and Ralph for your insightful comments as usual. In the next episode, Sunny will talk to Barbara Webb from the University of Edinburgh in Scotland. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Professor Gert Cauwenberghs. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript, along with direct links to the other stories we've mentioned and other resources. Thanks for listening.